Expected payoff and the local neighborhood equivalence. Our effort to succinctly model the CE of a graphical game consists of two steps. In the first step, we argue that it is not necessary to model all the correlations that might arise in a CE, but only those required to represent all of the possible expected payoffs outcomes for the players. In the second step, we show that the remaining correlations can be represented by a Markov network. For these two steps, we respectively require two equivalence notions for distributions: expected payoff equivalence and a local neighborhood equivalence. We shall show that there is a natural subclass of the set of O and CE of a graphical game based on expected payoff equivalence whose representation size is linearly related to the representation size of the graphical game. Definition 7.7. Two distributions P and Q over joined actions A arrow are expected payoff equivalent, denoted P EQQ EPQ if P and Q yield the same expected payoff vector. For each I, the expectations of Mi of A arrow, assuming A arrow is very close to P, is equals to the expectations of Mi of A arrow, assuming A arrow is very close to Q. Note that merely finding distributions given the same payoffs, as the C is not especially interesting unless those distributions are themselves CE. We want to preserve the strategic properties of the CE, not only its payoffs. Our primary tool for accomplishing this goal will be the notion of local neighborhood equivalence, or the preservation of local marginal distributions. Below, we establish that local neighborhood equivalence both implies payoff equivalence and preserves the CE property. In the following subsection, we describe how to represent this natural subclass in a certain Markov network whose structure is closely related to the structure of the graphical game. Expected payoff equivalence of two distributions is, in general, dependent upon the reward matrices of a graphical game. Let us consider the following more stringent equivalence notion, which is based only on the graph G of a game. Definition 7.8. For a graph G, two distributions P and Q over joined actions A arrow are local neighborhood equivalent with respect to G, denoted P equivalent L and Q, if for all player I and for all setting A arrow to the I of N of I, P of the distribution of P of A arrow to the I equals to Q of A arrow to the I. In other words, the marginal distributions over all local neighborhoods defined by G are identical. Since the graph is always clear from context, we should just write P equal L and Q. The following lemma establishes that local neighborhood equivalence is indeed a stronger notion of equivalence than expected payoff. Lemma 7.9. For all graphs G for all joined distributions P and Q on actions. For all graphical games and for all graphical games with graph G, if P equal L and Q and P equal EPQ, then P equal EPQ. Furthermore, for any graph G and joined distributions P and Q, there exist payoff matrices M such that for the graphical game GM, if P not equal L and Q, then P not equal EPQ. Proof. The first statement follows from the observation that the expected payoff to player I depends only on the marginal distribution of action in N of I. To prove the second statement, if P is not equivalent L and Q, then there must either a player I and a joint action A arrow to the I for its local neighborhood which has a different probability under P and Q. Simply set mi of A arrow to the I equals to 1 and mi equals to 0 elsewhere, then I has a different payoff under P and Q, and so P not equal EPQ. Thus, local neighborhood equivalence implies a payoff equivalence, but the converse is not true in general, although there exists some payoff matrices where the converse is correct. We now establish that local neighborhood equivalence also preserves CE. It is important to note that this result does not hold for expected payoff equivalence. Lemma 7.10 for any graphical game GM, if P is a CE for GM and P equal ln Q, then Q is a CE for GM. Proof. The lemma follows by noting that the CE expectation equations are dependent only upon the marginal distributions of local neighborhoods, which are preserved in Q. While explicitly representing all CE is infeasible even in simple graphical games, we next show that we can concisely represent in a single model all CE up to local neighborhood and therefore payoff equivalence. The amount of the space required is comparable to that required to represent the graphical game itself, and allows us to explore or enumerate the different outcomes achievable in the space of CE.